great pleasure to be here. I still remember the first time I visited Twitter. That was when Twitter was still in the South Park office with all of 25 people, including half of them ops and half of them engineers or something like that. So it's been a while, and it's definitely have grown up a lot. So this is the first time in this building for me. And yeah, it's wow to see sort of this development of Twitter from the little startup to this very significant company. So thanks for the invitation. I thought I'd give a tech talk here, which is sort of a more specific topic, because I guess you all know Scala. I don't have to sell you on Scala or anything. Of course, I'd be happy afterwards to take questions about essentially where we're headed and what new developments I see and things like that. That's a bit more speculative. So what I want to talk about today is about binary compatibility. And it's something where we haven't been doing so well. So wearing the hair shirt that we say, oh yeah, my God, we're guilty, guilty, guilty. Binary compatibility in Scala, that's really a difficult story. It's been an issue with Scala actually ever since it became popular. So about ever since Twitter adopted it in like, when was that, 2008. Of course, it causes grief when building, it causes friction for upgrading, you have to sometimes stay on old versions. And I think it caused that, it accelerated a development that essentially was natural for Scala at this development anyway, that to become more conservative. So it makes it harder to innovate and improve. It's a kind of a very tough choice. You either say, well, we're gonna improve, we're going to have a better system, we're going to fix design shortcomings and bugs, but at the same time we have to break client's code, or you say, well, no, client's code is sacred, we leave it alone, and then there's a lot of innovation and improvement that you can't do. It's sort of a very uneasy choice to have to make. So the question is there really no third way what we can do? So just to explain quickly what binary compatibility is. So binary compatibility is not the same as source compatibility. So what you would have here is an object server with a message val and a client that just uses that. And then let's say in the server you decide this thing should really be an option, and then of course that thing would break because you can't take length on an option value. So here you have an example which is actually binary compatible but source incompatible. So you have the server side here, you have an object with an implicit definition f, and on the client you import both both a and b, and you do this thing here, you assign 1 to a string, which of course you shouldn't do, so this is a completely synthesized example. So I don't recommend anyone to write an implicit conversion like this one here, but just for the sake of the argument. And let's throw in another one which essentially does another conversion from int to string. So if you do that, then if you run the binaries, nothing will happen because the implicits have been resolved already. But if you recompile client, then the next recompile will say, no, you can't do that. It's an ambiguous implicit. So that would be a source incompatibility. You can't recompile, but as long as you don't recompile, everything is good. But after these things, let's look at what the binary incompatibility would be. So you would have, let's say, a trait. So that's a typical example with a method. And now you add, so the trait is edible, the method is joules. And now you add another field, calories, to say calories is joules times 4.184. And now if you have this client apple, so an apple is an edible, and it defines what the joules method is. Now, if you compile these two together and then you migrate edible to this thing here, so it gets this calories method, you will have, up to Java 7, you will have to recompile apple. In Java 8, it's more complex. So in Java 8, there will be cases, hopefully many cases where you won't have to recompile, but unfortunately there will remain some cases where you do have to recompile. So the trick in Java 8 is we can use default methods to actually avoid recompilation in many but not all contexts. So why is this so? Well, if we have a look at the compilation of this trait edible, then that's what the Scala compiler actually would spit out. So since traits are not native to Java, what we have to generate is an interface. So in Scala, I'm still staying in Scala notation here, there will be just a trait with only abstract methods. And then I have an implementation of this calories thing, which essentially takes this as a parameter, and it contains the implementation of the method. Now on the client side, what we need to do for this apple, we have to look at the trait and say, well, what concrete methods does it have? That's the calories one. We have to install a forwarder in the Apple object that says, well, if you call calories on the Apple object, then what you really should do, you should go and call this static method in the edible class. So that's the implementation of essentially concrete methods in traits in Scala. So the big problem there is that if initially you didn't do this, so there wasn't a calories method, then of course the compiler wouldn't have done this. So it would just essentially create an object that defines the joules method, but not the calories method. And that would give you an abstract method error because, of course, seen from Java, this trait has two abstract methods, calories and joules. Okay, so there are other issues. That's not the only one, so that's one of the prime examples. There are many issues actually where compiler optimizations and bug fixes also can affect compatibility, and that's where it sort of hurts with innovation or with bug fixing. So an example of that are lazy values. So let's assume we have in this trait a lazy value, sorry, this should call lazy val, not def calories, but lazy val calories. Then what we need to do actually in the implementation is something more complicated. Essentially, we have to maintain a bit set that essentially contains the bits of the lazy values that we have already defined. And that way we can keep track of which lazy values were initialized and which we still have to do. So previously what we did was we had 1 bit per lazy value that essentially tracked the initialization status from uninitialized to initialized. So the idea was to say, well, if you have a lazy value, if we want to get the value, we check the bit. If the bit is not set, then we compute the initializer of the lazy value. We set the bit and we're set. The problem happens when you do this in a multi-threaded context. And you might have many threads that hit on the same value. So what we needed to do is while the computation was going, the object was locked. You couldn't get at the object. And the problem with that is that once you grab a lock, you might always interact with other locks and you might get into a deadlock. So there are situations where this can happen, that you get into deadlocks because of lazy values, which of course is not very pretty. So we have a fix for that, and the fix involves having essentially 2 bits. So we keep track with 2 bits about the state. So the state could be uninitialized, initializing, and initialized. And that means that we can have very short critical sections that just essentially check this bit. If you hit the second time an initializing object, you just say, okay, I want to be notified when that object is initialized. And once the object is initialized, you get woken up. The advantage is you have very short critical sections which we can bind, which cannot possibly cause a deadlock. The disadvantage is now we need 2 bits per lazy val. So it means all the layouts of our bitmaps change. So if once we do this, then we break binary compatibility in a very insidious way, because essentially programs look still type correct, but you will hit the wrong bits in the bitmap. A very unpalatable situation to have. Okay, so if we look at what actually happens in a compiler, then what you have typically is a fairly long compiler pipeline that goes from Scala to something that essentially first resembles Java syntax trees and then finally Java bytecode. And I'm just throwing this up here to sort of give you an idea what goes on here. Each of these things does a meaningful and sometimes complicated transformation. So a lot of things can go wrong here, or a lot of design decisions can be decisions you want to revise later on. You want to do something else later on. Okay, so lots of scope for things to go wrong here. And that makes the binary compatibility problem hard. So what's so bad about binary incompatibility? So where it breaks is that if you have, let's say, a dependency like from A to C, and you produce C with C.Scala, that if you have a source binary incompatible source change, then you produce a new class, and if you want to combine then the old client with the new provider, then you get a crash, or you get essentially the program won't load, and you get a binary incompatibility error. Okay, so that's the situation. Why is it such a big problem, in particular as organizations and code bases grow? Well, let's say you have your shiny application and it relies on some dusty legacy libraries. These things happen. Some people worked 3 years ago on some things. It's still in service, but nobody really knows anymore quite what this thing did. But anyway, it's in your code base. You can't rewrite this all the time. So you use that. And then, of course, that dusty legacy library would use the Scala library, like 210. And let's say you do sequence.scala in 210. And let's say we decided in 211 that we want to rewrite sequence.scala in a binary incompatible way. So there you go, binary incompatible change. Now the problem is, this thing, nobody really remembers how to build this anymore. You have the class files, that should be enough, right? So what do? Well, the problem then is, once you have that, you can't upgrade your application to Scala 211 because, well, it relies on this thing and you can't bring this thing over. So you have the situation. And that's essentially the insidious problem of binary incompatibility, that it holds organizations back. You say, I have this dusty legacy deck, which you always have. Any organization has that. And that's sort of poisoning the whole well. So I can't really go and upgrade my application independently of that. And of course, it's not just the problem with the Scala library. It's just most common in the Scala library. But let's say if you used Akka or Finagle or any of the other libraries, and you upgrade and it has a binary incompatible change, then it's exactly the same. That works for Scala or Akka or Shapeless or whatever. Any library you use has the same problem. It's just that Scala gets hit on it most because everybody relies on the Scala library, so everybody sees the problem in the Scala library first. So how do we deal with it so far? So we have this migration manager tool, MIMA, that can at least detect binary incompatibilities. So that's already a big step forward, because it now means that we can actually have a policy that we can check, that we can control, that at least minor versions must be binary compatible, backwards and forwards going. And we have had this policy since, I think, 2.10 or 2.11, I'm not exactly sure, but now for a while already we have this policy, so with minor version changes, there's nothing to fear. Major version changes are allowed to break binary compatibility, because otherwise we would reach stasis and couldn't change anything, but they tend to be released more rarely these days. So typical interval between major versions are maybe 18 months or something like that. So the problem with that is that third-party libraries need, of course, similar policies, but often they don't enforce them because they're new to the problem, then they're not really aware of that problem yet. So you have more and more stuff that actually breaks in third-party libraries. And even if everybody was disciplined enough, then innovation would be stifled. Simple fixes have a long time to get in, and lots of dev cycles are spent on dealing with binary incompatibility. So it's not a nice situation. So you can ask, well, if it's so difficult, then what do others do? Why is it a Scala-specific problem? Is it just that Scala compiler writers and library writers are a lot less disciplined than in other languages? I don't actually think that's a problem. So let's have a look what the others are doing. Java has it much better. So the language is very close to JVM bytecode, so there's very little scope for binary incompatibilities to creep in. And furthermore, if there is some problem, then Oracle, the Java stewards, have always the option to change the VM. And they do that. So they do change the VM to paper over problems that would manifest themselves in binary incompatibility. So for instance, in Java 8, you have the lambdas and default methods. That's JVM changes. That's also compiler changes, but the deeper changes are in the JVM. The other approach is to say, well, libraries are frozen when they appear, and you'll never upgrade them. We have Java util date to this very day, and of course it sucks, and of course there are 3 better options, but well, let's have all of them, and let's just keep the old stuff so that nothing will ever break. And furthermore, finally, the language is quite restricted in terms of extensibility. That's gotten better with Java 8. But until now, the trait problem that I mentioned in Scala, the recommended usage would be to say, well, never add anything to an interface, have versioned interfaces instead. So in Eclipse, you find like some interface with version numbers 1 to 7. And each of the interfaces has more and more methods, but then essentially you offload the whole problem to the client, the user of those interfaces that has to say, well, if it's a newer one, then use this optimized methods, otherwise fall back to this code. Not pretty. Okay, so that was Java. The other thing that a possible solution to the problem would be OSGI. So OSGI allows multiple versions of a library in an application. So there you could actually say, well, if we have the same migration scenario from 2.10 to 2.11, you could have just rebuild your application and not touch just the legacy lib. And then you would just run the whole thing with the 2 versions of the library, which happen to be in different OSGI containers. It requires a lot of work to make this happen correctly. It requires serious class loader magic. It's quite fragile. And some frameworks use that, for instance, Eclipse, but very few frameworks beyond Eclipse have bought in here. Okay, so that was the Java world. What about C++? Well, C++ relies on a linker for more flexibility of interfaces, and it's not really that great a story either. So the name DLL hell doesn't come from nothing. What about Clojure? Well, Clojure builds from source. JavaScript, built from source. Python, built from source. Ruby, built from source. Go, built from source. Okay, so it seems we have a clear winner here. So, so why can't Scala build from source? Well, I think it's sort of historically the way Scala has grown up. So in the Scala world, you don't have a standard build tool. There's something, of course, there's SBT, but not everybody's on SBT. You guys are on PANS. I don't even have that in the list. Other people are on Gradle or Maven or Ivy or Ant even. That means that it's much harder to essentially do a reproducible build. And the other thing is, even if we would agree on the same build tool, then still the culture is that reproducible builds are really hard. It's quite hard to make I mean, we have now this effort of the community build, where we built, I think, now close to 1.5 million lines of community sources on each night when we do that. And it was very hard to set that up, to actually include something in the community build, because, well, all the build conventions are different, the config files come from different things, and so on and so on. So it's a chicken and egg problem. Because everyone is used to binary compatibility in builds, nobody invests in making builds reproducible. So nobody, not quite true, we have invested in the community build, and that's a big thing. Good. So how to progress from here? So I think what we need is an interchange format that captures the essence of Scala dependencies without caring about what bytecode is, what the eventual output will be. So in a sense, it's a declaration of independence. And it can't be the JVM bytecode format, because that bytecode format is too low level. There's all the scope for binary incompatibilities that can creep in. And it can't be source either, because there are no reproducible builds. So the idea is to use something in between. Christmas is past, so I still thought this was nice as a type tree. So to use a type tree as an interchange format. Type trees are much more robust than source, I'm going to argue, and much more stable than JVM bytecode. And the question is, will they be efficient? So I'm going to talk about that. So in the new compiler pipeline, it would look something like this. So there would be the front end, which has the parser, the typer, and then some phases that essentially do some sort of normalization on the tree. And then you would have essentially cut off here and say, well, what we produce now, at this point, we would essentially produce symbols and types for separate compilation. We would tell what symbols and types are in a source file. And now we would produce more. We would give you a complete view of this using type trees. And then the whole backend would use the type trees and produce bytecodes. And of course, there would be a fast path that would spit out the tree, but also go directly into the compilation pipeline. And so you can go into bytecode with using just a single tool rather than two tools. Okay, So how would that affect our builds? So what we would have now is we would have essentially, here's a typical example of this 3-layered thing. So we would have A, B, and C, and they depend on each other. And what we would have is, as the artifact of these things, we would produce a Java class file, or many class files typically. And we would also produce a tree, which is called A tree, B tree, C tree here. And we would produce a hash of the tree, which essentially says what the tree is, and also what the class file is. So if we now have a source change, then that would give us a new tree with a new hash down here. And what we could do then is to say, well, let's say we have this. We import the jar that contains this C class. So maybe that's a part of, again, Scala 2.14 or something like that. And now we want to say in the client, rebuild. So what the client would do is it would say, well, I rely on class B. Is that still up to date? So I look at the dependencies of this class, which I essentially also captured here with the hashes. And I say, well, no, this class is actually not up to date. It has a newer class. No, sorry. This class has a newer hash, so this class is not up to date. And then essentially the build tool would say, let's rebuild the class B. And the build tool typically doesn't have the source of this, but it doesn't need to, because it can produce a new class file from the old tree here using the new dependencies. And that class file will typically be not the same as that one here, because it uses different dependencies, and that will affect the bytecode. So once we've rebuilt B, then we can rebuild A. And all these things can be done automatically, essentially very similarly to how we do the incremental compiler from source. Only the difference would be the incremental compiler has the source of everything, and here we only need the classes and the trees and not the source files. Okay, so how is this better? So the first thing is, why not use source? I said already it's source is fragile. In particular, the early phases, they have to do a lot of tricky business. So they have to resolve the names, every reference that you have, which means they have to scan your class path, they have to scan your packages, that has to be reproducible, they have to handle imports, they have to establish implicit scopes, so you throw in an implicit in a new version of the project and everything might change, right? Have to resolve overloading, find implicits, apply conversions, infer type parameters, and finally assign the types to trees. So a lot can go wrong in these things, and that makes reproducible builds so hard. In the new scheme, what we would have is that we say, well, we have these type trees, and for compactness reasons, it will turn out that the trees essentially give you the types only at the leaves, and you have to reconstitute the types of the internal nodes, because otherwise they would be too large. But the module that does that we have is currently 311 lines of source code. So it's not at all of the complexity of a full compiler front end. It's something that you can have a lot of trust in that it will work reliably every time. It's a lot more resilient than bytecode, because now essentially all the examples that I've shown you and many, many more wouldn't present a problem at all. We can freely add fields and methods to traits. We can add lazy values anywhere or change the format. We can change the compilation scheme in any way necessary. So anything that happens here, we can change at will in the new version and not affect binary compatibility, because it can be redone whenever something changes. Okay, the remaining question is it efficient? So one immediate objection would be, well, if you have 1 million lines of code, wouldn't these trees become impossibly large? And if for large trees, the related question is, wouldn't the transformation times of these trees become impossibly slow? So if we look at the size first, so here we have a typical example. So here we have a small source expression xs.filter underscore greater or equal 0, 17 characters. And that's essentially the tree that the compiler spits out for that. So you see this quite substantial. So it has 16 nodes, not counting the types. So if you then do like a back of the envelope calculation, say the average size of a node is maybe 32 bytes. You have 512 bytes, double that to include the type info. So that means that 16 bytes of source will give you a 1 kilobyte tree, a factor of 64 blow up. So for a 1 million line system, you can maybe count 30 megabyte source, something like that without the comments. That would give you 2 gigabyte of trees. And that's a bit large. Fortunately, there's a lot more compact information, compact representation that we're currently developing. We call this format the TAST format. That means that we can actually get down here to something that is much, much more compact. So this thing here contains for every tree essentially the total size of the tree. So the whole thing here is of this serialized representation is 34 bytes. Okay, so that means that now we are sort of one 30 megabyte source would maybe give you 60 megabytes trees, which is not at all out of line with the size of the class files that we generate anyway. So I think that can be handled well. Speed, so transformation bytecode generation currently amounts to about 60% of total compile time. There's a lot of tricks we can use to speed that up. So we have experimented with fusing phases, reducing the amount of intermediate trees, using fast type assigner rather than the slow typer, full typer. And what we also can do is we can actually build different files in parallel, because once we have all this information ready, there's no need to actually have a sequential compiler that goes through these things one by one. Besides, of course, we can use incremental compilation, so compile only units that depend on change libraries. And finally, of course, as long as nothing changes, as long as your hashes are still okay, you don't need this thing to produce the bytecode. So the build would be incremental. It would only essentially recompile what it has to do. So again, this looks pretty manageable. Okay, so type trees seem to be a very good solution for the binary compatibility challenge. But in fact, they have lots of other benefits as well, and that makes people quite excited about them. So the first thing is they're a great format for interprocedural analysis, data flow analysis, things like that. So whether the data flow analysis, you could use it for optimization. So for instance, for very aggressive fusion, so in the style of, let's say, Scala Blitz, that fuses collections to get orders of magnitude speed improvements. Or you could use it for analyses like security checks, security analyses, other style checks, well, deeper than style checks. You could, for instance, detect reliably that certain patterns that are dangerous, like in actors, there's a problem that you are not allowed, that essentially closures that see fields that are mutable, so they might see them at the wrong time and things like that. So a lot of these sort of dangerous patterns that we have grown up to know in Scala can actually be detected reliably with interprocedural data flow analysis. Without the type trees, all we could do is essentially a local analysis that looks at the local code only, and of course that would miss a lot of things where actually the dangerous patterns goes over several layers of methods. We can also do very aggressive inlining without any binary compatibility issues, because again, we can redo them as we need. We can use a lot of better program analysis, so for context-dependent program analysis or instrumentation. And finally, it will be a great aid for portability, because now it will become possible to publish a single library and have it run on the JVM, but also on, let's say, Scala.js on JavaScript and on any other backend that will be developed in the future. So all these things have people being quite excited about them. Question is, how are we proposing to actually get this into Scala? So the type trees effort is actually part of this dot effort that I have started with my team at EPFL, but we're now working with the Scala team at TypeSafe to make this happen. So what we plan to do is actually have, besides the old backend, a new backend that would be backed by these type trees, and we would have essentially common compilation pipelines from the Scala C frontend and this new experimental .c frontend. And then those type trees also would ensure the interoperability of Scala C with .c, and we would use the Gen B code typer that is currently essentially Bytecode code generator that's planned as the code generator for Scala 2.12 as the common backend, and that is used by both the old backend and this tentative new backend. So that's a bit of what we have as a roadmap here. So to conclude, type trees can fix the binary compatibility problem, and they offer lots of other benefits too. So what we are about to do and what I would invite people to join us is to start the work to make them real. Thank you.